Okay.
Sir, I have one small question.
Yeah,
Can
sure,
I
sure,
ask?
sure.
While defining change of parameters, why
Hmm.
did we say that the derivative should be strictly greater than 0?
We said greater equal to 0 actually.
Um,
Uh, Greater equal to 0. So it's non-decreasing.
why
So
do we need this?
uh, that is because how do you make change of variable, right? Uh, Change of parameter. So this is nothing but change of variable in the integration, right?
Yes.
So what happens if it is 0 at some point? So derivative, see, it's going from closed interval, let's say alpha beta, to closed interval AB onto, right?
Yes.
So after going further, you don't want to come back, right? Because I mean, uh, generally this is what we want. So what does it mean? Let us check. So suppose, so there is a discussion. You have an interval, let's say alpha beta, and from here you want this to go to AB, and from here you have this curve gamma inside C, right? Now, of course, this well, first of all, of course, either alpha would go either to A or to B, right?
Yes.
All right. So if you assume this goes to A and this goes to B, so that means if you look at the curve here, we'll call this was gamma A and this was gamma B. So now alpha would go here, right? So alpha would corresponding to here. So if you compose, if you look at this composition and call it sigma, then sigma would, this one would be sigma of alpha, and this one would be sigma of beta, right? So you want to keep the direction of gamma to be same, right? So from here, this here, from AB to C, when you define gamma, it goes from gamma A to gamma B, right? Not the other way around.
Oh, we want to preserve orientation.
Right, right. So you
Okay,
want
okay.
to preserve the sense.
Sense
Okay.
preserving.
Yeah,
Okay, got it.
yeah.
And we don't need this map to be 1-1. Only ontoness is fine.
Right. Only ontoness and this non-decreasing part actually gives you kind of one, right? Isn't it?
Yeah. Okay, yes, it gives.
Yeah.
Thanks.
Okay. Any other question if you have?
No, sir. Strictly increasing will give 1-1.
Right.
Yes.
Strictly increasing will give you 1. And what if it's not strictly increasing?
It may be that some portion is constant kind of things.
Some
So
portion it is constant. Then what happens?
then we can have a same functional value for two distinct points.
Okay, but well, this is fine. This is a little bit of let's suppose this one goes to a constant value here. It's possible. It doesn't actually matter. So then you basically consider this point as equal to this point. Doesn't matter basically. This might happen that this in the middle of this one, it is the same point. So these 2 points alpha and beta would go here, and in between whatever it goes there only, and the rest part it will be the image of this segment will be image of this one. Yeah, sorry. right? So yeah, image of this one and image of this one will be this. All right. So if this happens, then also it's fine. So, but it's basically kind of what would I say? So pathology, considering this point equal to that point, is good enough. For example, I mean here it doesn't matter. So what we are considering. So here also, if you integrate, you will integrate this part and this part. This part would actually will not give you anything, right? Because it goes to a single point in the curve, and it's coming to a single point in the curve. So that's how this can happen, but this actually it's a pathological case. You don't need to consider as such. So in some sense, we are looking at the parts mostly where it is 1-1. All right.
Yes, sir.
Okay. So any other question? Okay, then. So Basu, shall I just start?
Yeah, Sushil, you can start.
Yeah. Okay. All right. So this is lecture 2. So first thing I would like to mention here is reversing direction. The direction of a curve gamma. So what does it mean? It means, so you have 2 points. Let's say this is and maps from a closed interval AB. So this is gamma A, gamma B, and you have a curve. So, and it's of course going from gamma A to gamma B. And so reversing direction would be coming along the same curve. So, coming along the same curve, but along the opposite direction. Oh, what happened? Can you see my screen?
Yes, we can see your screen.
Okay. Yeah, so something opened, some folder opened actually. Sorry for that. Yeah, all right. So here it actually it reverses. That is what it means to be reversing the direction. Let me make it precise. So which means, so gamma is a curve from AB to C, is a curve, then minus gamma, which will be from minus B to minus A to C, defined by minus gamma of T is gamma of minus T. All right. So this starts from gamma B and reaches to gamma A. Right. Now look at the question. Yes.
Sir, it would be minus B to A, minus A or B to A.
No, this is fine. Minus b to minus a.
Fine. Okay.
Yeah, because you see the definition, gamma of minus t, when it is minus b, at minus b, it is gamma of b, right? So it is this endpoint, this point. And when is gamma is minus a, then minus gamma of minus a is gamma of a, which reaches here, right? So how does it behaves with the integration? So how does this behaves with integration? So that means what is the relation between? So that means how this the integrals integration gamma f dz and integration minus gamma f dz are related. So this is the same question, right? So let us answer that. This is of course very simple. So we look at integration over minus gamma f dz. Now we unfold the definition of integration, which is from minus b to minus a. Minus b to minus a, f of minus gamma of minus t, right? So gamma of t actually, what did I write? What was it? Minus gamma of t. So minus gamma of t minus gamma prime t dt. All right. Now what is it? Minus b to minus a, f of gamma of minus t. And what is minus gamma prime t?
Minus gamma prime t.
Right. Minus gamma prime of minus t. Right? dt.
Oh, yes, yes.
Right? So this is so minus gamma is defined as gamma of minus t, and then you are taking derivative. So that means gamma prime of minus t, and then minus will come, right? So now we make a change of variable t to minus t. So what do you get? Yeah, a to b. So change of variable. So you look at minus t to t, right? So then it will be from a to b, f of gamma t, and here gamma prime t, right? And what will be it?
Minus dt.
Right. So this is minus dt, but here look at these things. So gamma prime of minus t. So gamma prime of minus t and you are making a change of variable, right? Minus t. So will that just be gamma prime t, or there will be a minus sign?
Sir, minus sign is
Right. So minus of gamma prime of t, right? After change of variable. So this is after change of variable. So this minus and this minus goes away, so there will be one minus. So minus a to b f of gamma t, gamma prime t dt, which is nothing but minus of integration gamma f dz. Okay. Is
Sir.
this fine? There is mistake.
Sir,
Yes.
sir, explain the second step, second line.
This one?
Yeah, second line, yes.
Right. So you are making a change of variable. Maybe let's look at, instead of looking at t, let's call it s. Okay. So you are looking at s equal to minus t, right? And then you make this change. So let me just erase this part and see what happens. So your change of variable is s equal to minus t, right? So integration will be from a to b, and gamma of minus t will be s. And here there is a minus sign, right? So let's just, yeah, this is fine. So here, what will be?
Sir.
Yes.
So from second to third line, if we change minus t, change the variable minus t to s, so the limit will be b to a. Then the negative sign will change. Then a to b will be happen.
Oh, okay. So that's how.
Yes,
Okay.
sir. Yes.
All right. All right. Yeah. Yeah. Thanks for this. Hmm. Hmm. So it would be b to a. That is correct. This I was missing. B to a. Right. So here it is fine. So that part does not change. Gamma prime of s, and here will be on a minus ds. So this is not true. We are not taking derivative after change of variable. So this one will give you a to b, and there's minus. So f of gamma s, gamma prime s ds. Is it fine now?
Yes, sir, not fine.
Okay.
And sir, minus
I
gamma
think
dash.
one minus is taken care already. So minus ds is not necessary. ds is fine.
No, this is from b to a, so there will be a minus. So then, so if s is equal to minus t, ds will be minus dt.
It is okay, sir. Okay, it is fine.
Yeah, it's fine. It's fine.
Yeah. So this is fine. The only point is, if you here, we are not taking derivative after using the s. We have already derivative. We just make a change of variable. That's it. So here there will be no minus.
And sir,
Yes.
derivative of minus gamma and first line. Minus gamma dash t is minus of gamma dash minus t. So
yes. Oh, so this is so what is gamma? minus gamma of t
and gamma.
minus t, and you take derivative.
Okay.
Right?
Yeah. Yes.
So gamma prime of minus t, and then there will be minus.
Yeah. Right. Right.
Okay. All right. So this is important. This will be using. Let me switch on the light. Just 1 minute. 1 second. All right. Okay. So we'll actually let me mention briefly what is the length of curve. So integration with respect to arc length. Right. So here, so arc length FDS is defined as integration over gamma f mod dz. Right. So what is mod dz? Well, I'll come to it. So mod dz, as you know, dz is dx plus iy. So mod dz would be square root of dx square plus dy square, so on, which is nothing but ds. So this will be nothing but integration a to b f of gamma t mod gamma prime t dt. Right. So this is integration with respect to arc length. And what is length of the curve? So suppose gamma is a smooth curve in C. So what is what is length of the length of gamma? So what is it? Integration. Excuse me, I need to take a call. Yeah, I'm sorry for that. So what is the length of the curve gamma? Length of the curve gamma. Gamma is a smooth curve.
It have to be 1.
Right, have to be 1. So this is mod dz, which is nothing but mod gamma prime t dt, right? Yeah, which is nothing but integration a to b integration over gamma mod dz. All right. So an exercise. So this you know as ML inequality. I'll just put it in this way so that integration gamma mod of fz dz is less or equal to integration over gamma mod f mod dz. So if f is bounded by capital M, so this will be less or equal to m times L of gamma, where provided mod of f z is less or equal to m for all z in gamma is good enough. So gamma is trace of gamma here, and f is continuous. Given here, given f is continuous on gamma. Okay. Yeah, this is fine. So we'll go into the dependence integral, which depends only in points now. So the question is, next question is, suppose, so it is question in R2. Suppose gamma is a curve in R2 and P, Q are two continuous functions. Well, here what we need is continuously differentiable functions. One is p dx plus q dy. One is this integral depends only on the endpoints of gamma. See, this is a question in R2. Oh, sorry. This is a question in R2. There is nothing to do with complex analysis here, right? It's just p dx plus q dy, which you integrate over path or over a curve in R2. Well, you can take smooth or piecewise smooth curve. And this question whether integration p dx plus q dy depends on the endpoints of gamma or not. That is the question, valid question. So let's see the answer to this one. So what do you think the answer is?
So if the functions as primitive,
What does it mean to be primitive here?
there is some function whose derivative is this function.
So this here it is p dx plus q dy.
Exact, the gradient.
That is true. In some way, that is gradient looks true. Okay, so let me write it. Yeah. So theorem. So the line integral. So this is called usual line integral, right? Integration over curve gamma and p dx plus q dy. Integration over gamma p dx plus q dy defined. So pq defined defined in an open set omega in R2 depends only on the endpoints so here you see, which means the line integral, this one defined on an open set means the line integral of over any curve in omega endpoints of gamma if and only if there exists a function u from omega to r such that del u by del x is p and del u by del y is q. All right, this is what somebody means to be gradient, right? So p comma q is a gradient of a function. So is the statement clear or is there any confusion? So this is a very important theorem. We will apply in the context, in our context, in complex analysis, this theorem and see what we'll get. Any question about the statement?
Okay.
All right. So let's go into the proof then. First, the easy part. So given there exists u from omega to r such that del u by del x is p and del u by del y is q. So here you see the regularity, it's continuously differentiable. So C1 is C1. So to show integration over gamma p dx plus q dy depends only on the endpoints of gamma, where gamma is a curve in omega. All right. So you are given a function where del u by del x is p and del u by del y is q, and you have to show this integral p dx plus q dy depends only on the endpoints of gamma. All right. So now look at this one, integration over gamma p dx plus q dy, which is nothing but integration over gamma del u by del x times dx plus del u by del y times dy. All right. Now you unfold the definition of integration. So this is integration a to b. So gamma is a curve from ab to omega. So ab del u by del x gamma t gamma 1 prime t. So you see gamma of t will be gamma 1 t comma gamma 2 t, right? dt plus del u by del x of gamma t gamma 2 prime t dt. So what does it mean? Yeah.
So second will be del u by del x or del u by del y?
Oh, del u by del y, right? Mistake, yeah. Del u by del y. But what will it be? Then do you say chain rule?
du of gamma into d gamma. Like
U of gamma.
d of u gamma and then d gamma. Like,
Okay. Okay. So this is fine, but you can do it little better. I want ddt of something. Can you say what is it? I want it to be ddt of something, and then dt. So what will it be?
U compose gamma of t.
Right. So u of gamma t. So maybe I would write u of gamma 1 t comma gamma 2 t dt. So this is how it is. So you have closed interval AB. Look at this picture. Here you have omega. This is gamma. This was the curve, and u was a function from here u to r. All right. So you are looking at this composition, right? You compose gamma. So now use fundamental theorem of calculus. So using the fundamental theorem of calculus, we have u of gamma a, gamma b minus u of gamma a. All right. This implies the integral integration over gamma p dx plus q dy depends only on the endpoints. So if you are confused about chain rule, you can look at Spivak's calculus in manifold book. It is given more general form and very easy. Okay, so this proof is fine. Yeah, any question on this side? All right, I suppose there is no question.
Sir, omega is connected, right?
Yeah, if it is not connected, it will go to a component. Right? Gamma is a continuous map. So omega does not need to be connected. Only open is good enough. But since closed interval AB is connected, gamma is continuous, so image will lie in one component. So is this fine? Yeah. So open set is good enough. You don't need connectedness. So what comes here? That here gamma. So maybe I just comment if omega is not connected, gamma will lie in one component. Okay.
So why does this question of connectedness arise?
Well, it's basically it doesn't arise here at this point as the proof goes. So there will be no problem. The point is, see here, this gamma, if it is not connected, whether this, suppose omega is like this. So question is whether the half portion gamma lies here, half portion gamma lies here, right? Then there might be problem.
So it cannot be, right? Gamma is continuous and AB is connected.
Exactly, this cannot be, and hence you have no problem. So actually, it is enough to work with omega to be connected.
My question was, where do we need this connectedness part?
Well, we where do we need? Actually, in the proof we don't need, but since gamma is continuous, it goes into a connected component. That is the point.
Okay, it's just a fact, right? We are not using it anywhere.
No, we are not using it anywhere.
Okay.
Right. All right, so let's look at the other part, which is, so here given integration over gamma p dx plus q dy is independent or dependent only on depends only on the endpoints of gamma. And to show, there exists a function u omega to c omega to r such that del u by del x is p, del u by del y is q on whole of omega. All right, so the question in front of us is, what will be a candidate, right? How do you start? Right?
So px plus qy kind of functions.
Px plus qy?
Kind of functions where
Yeah, p and q are functions on omega. P and q are given functions in omega. That is given. So you have certain omega and so the question is, what would be the function u? A candidate. You need a candidate, right? So it is just the analog of fundamental theorem of calculus, right? So isn't it same, looks almost same like fundamental theorem of calculus, right? Since it was R, so derivative only in one variable, derivative was in one variable only. Right? So you what do? You fix a point. You fix a point here. Let's say x0, y0. Okay. So here comes the use of connectedness or the component of omega. So take any other point, xy, x comma y, and we want to join this 2 points by curve, right? So first thing is, what we want is, we want to join a curve, something like this. Something like this, right? So is there any problem if we use this curve? Any question?
Gamma has to be path connected space. Sorry, omega.
There's an open set. Each component is path connected, so there is no problem in there. So it is enough to work with one component, so you can use path connectedness. There is no problem here. So is there any problem if I take this kind of curve? There is no problem. I suppose there should be a lot of questions, right?
The definability at the
Yes,
eighth
sir.
point.
Yes, sir. Corner points are there still.
Well, gamma can be taken to be piecewise smooth curve. There is no problem. Did I write gamma to be smooth? Gamma is just piecewise smooth curve. So gamma here, gamma is piecewise smooth. Now the question is, can I take this curve?
Sir, maybe sir, partial derivatives will not exist.
No, there is no problem. The question is actually,
No, sir. Here, so this kind of three kinds of paths, right? So each time we shall have endpoints, and I think there will be six endpoints.
no, why should it be 6 endpoints?
First, consider this vertical part. Say it's gamma 1, then the horizontal one. It should be gamma 2, and then again the vertical one, gamma 3. Now we want, ultimately we want the point value at the point xy and x0 y0, right?
No, we want a candidate, define u, right? U of xy, actually we want to define. Right? The problem is whether this curve lies in omega. We don't know what omega is. I have drawn some picture, right? The question is whether this type curve will always work.
But sir, you said omega is open, so path connectedness is there. If not this kind of picture, but still we can connect it by some polygonal paths.
Right. But what else property we need? We need actually, so the line segment, each of the line segments should be parallel to axis. So here it is. So if omega is something like this, these are the axes, x and y. So this segments of the curve should be parallel to the axis. So first thing is join the point x0, y0 to xy and xy by polygonal path, whose sides are parallel to the axis, right? And let's assume the last segment is parallel to y-axis, right? Since it is an open set, we can take a small y-axis around in the end all the time. So if we cannot make like this by 3 segments, but we can do it by finitely many segments. That is always possible. All right? Is this fine?
Yes, sir.
All right. Now define a function as we did in case of fundamental theorem of calculus. So define a function u xy is integration over polygonal path gamma. So gamma p dx plus q dy. All right? It's a simple thing. You have to choose the right path. So path gamma is a path joining x0 y0 to xy, whose sides are parallel, which is polygonal, and each sides are parallel to axis, and the last one is parallel to y-axis. Now what we are given? We are given that integration is independent of choice of the curve. It depends only on the endpoints.
Sir, one question.
Yes.
Sir, why the last part should be parallel to y-axis?
Oh, that is my choice at this point.
Okay.
Right? So this is an open set, and you can take a small neighborhood and you choose the first line to be vertical.
That's fine. But my question is, if I choose that one to be horizontal one.
Yeah, next time we'll choose to be horizontal also. So first we'll take the vertical. So this will have some properties. So the first question is whether this is well defined, right? So first question is whether this is well defined. So U is well defined because the integral depends only on two endpoints, which is on x0 y0 and xy. All right. So x0 y0 is already fixed, so it depends only on xy. It doesn't depend on the curve. All right. So you will be well defined. So now let's come to the since we have chosen gamma in such a way that the last segment is parallel to y-axis, right? So you look at xy, and suppose each segments, or suppose the segments are gamma 1, gamma 2, gamma k, right? So this integration would be this gamma 1 p dx plus q dy, so on, plus the last one, which is integration of gamma k p dx plus q dy. Now this gamma k is vertical line, right? So it should be, so all these have some endpoints. So let the endpoints of gamma j be xj minus 1, yj minus 1, and xj, yj. For j, we start from 2 and to k minus 1. All right? And endpoints, and of course, you know the first point, you know the endpoints of gamma 1 and gamma k, right? Once these are fixed. All right? So is this fine? So integration over gamma k p dx plus q dy. Look at this one. So this line would be vertical. So x will be same as gamma k minus 1. So what will be it? Yeah, it will be,
X.
let's say, x k minus 1, y k minus 1 to x k minus 1, or maybe, yeah, it's rather, sorry, it should be vertical, so it will be x comma y, and here x comma y k minus 1, right? So this would be vertical. So here xk minus 1 will be xk p dx plus q dy. So note xk minus 1 will be x here, since this gamma k is vertical. All right, so what do you want to do next? You want to take derivative with respect to y. Or with respect to x, right? No, yeah, with respect to y. So x is fixed here. So see all the segments. So you want to take the derivative. So we want del u by del y, right? So look at here. Which integrals actually depends on y? Can you tell me?
Q dy part.
But which part? Does it depend here?
Last.
Exactly, the last one. Does it depend? This one? It does not, right? Because it has some endpoints different from xy. So it depends only on the last one. So del u by del x, del u by del y will be, well.
Sir, can you repeat this again?
So yeah, maybe you can look at this example, right? You have x naught y naught. Let's call it here. So what would be this one? This would be, let's say, x naught y1, and this should be x1 y1, like this, right? So here this is a vertical segment, depends only on this x naught y naught and x naught y1, right? It does not depend on, after integration, it does not depend on y. These are constant, right? So this part does not contribute. So the first part does not contribute. So this part does not contribute here, except putting some constant. So the other part also does not contribute. only the part contributes is this part, right? This part only, because here you have dependence of y, right?
Okay, thanks.
Yeah, this is just analogous to the fundamental theorem of calculus, but in two variable. So when you take the differentiate with respect to y, the all other part goes away. So the only thing is, well, first you should actually, I should write it in a, as what I said, I should write it. So which means this uxy is the last integral, which was what? Integration yk minus 1 to y p x y dx plus q xy dy plus constant. So this constants comes from each of the integral here. All right. So this one, del u by del x gives you, by fundamental theorem of calculus, this is what? Can you tell me what it is? So here, if you integrate, x is constant, right? X is always there, so it does not, actually it is independent of x as such, right?
Q but only come.
Yeah, qx will come. So here dx will be 0 on this vertical lines because x does not change. So here it would be integration. So this one, maybe this one I should write once again. This one, integration yk minus 1 to y q x comma t dt, if you change the variable here y, plus constant. So now we get in terms of fundamental theorem of calculus. Now apply the fundamental theorem of calculus. Here what you get is again the constant. Well, del u by del y is q x comma y, right? Constant derivative of the constant will be 0. Is this fine? So we need to reach this one. Okay? And to reach this one, we actually needed the vertical. So if we take the last component to be last part of the curve gamma to be horizontal, we will get x to be changed and y to be fixed, right? So similarly, considering a curve piecewise smooth, gamma, whose, well, polygonal curve. So I should mention that one. Polygonal gamma whose sides are parallel to axis and the last segment parallel to x-axis, then following the same procedure, we get del u by del x to be pxy on omega. So the point is here you have this omega, and what we wanted, which Actually, this is x0, y0, and here xy. So we take whatever curve we like. But the last component should be horizontal. Okay? There you will find this. All right, any question here? It will take some time for you to appreciate, but this is the fundamental theorem actually. The generalization of fundamental theorem of calculus in R2. Right? And we now see what happens if we apply this one to, in our case, in complex variable. Okay. So let's call it theorem. So let's call it theorem star. So now an application. So consider f to be u plus iv. Okay. Continuous function on omega. Suppose integration af over gamma dz depends only on the endpoints. Then what happens?
Each individual u and v also depends on the endpoint.
No. That's not correct thing. So what is integration of gamma f dz in terms of u and v? This we looked at last time. This is gamma u dx minus v dy plus I integration over gamma v dx plus u dy, right? Where gamma in the right hand side viewed as a curve in R2. All right. Now this individual, this one depends only on the endpoints. What does it mean? Yeah. So by theorem star, integration over gamma u dx minus v dy and integration over gamma v dx plus u dy depends only, well, this is not application. So this is by assumption. Depends only on the endpoints of gamma, right? So what does this mean? Now apply by theorem star. There exists a function f, right, from omega to r such that del f by del x is u, del f by del y is v, right? Or minus v for the first integral. Okay? This is called this maybe 2. And there exists g from omega to r such that, actually C1, such that del g by del x is, see here, v, right? And del g by del y is u. V and del g by del y is u on omega. Okay? Now you have some equation, right? See here, you have u and v, u and minus v, and here you have u and v and u, right? So let me write them together. Del f by del x is u, del f by del y is minus v, and then here del g by del x is v, del g by del y is u, right? Yeah, is this fine? Now what is del by del x of f plus ig? Oh well, let me just first show you something else. So what is this equation? Del f by del x is del g by del y, and del f by del y is minus del g by del x. Do you recognize this equation?
Kind of CR equation of a function f plus ig.
So these are Cauchy-Riemann equations for h, which is defined as f plus ig. H, which is f plus ig. Now this actually, what is del h by del x? So del f by del x plus I del g by del x. So what is it? Del g by del x is v, del f by del x is u. So u plus iv. So can I write? So this one is nothing but f, right? Yeah?
Yes, sir.
Yes, sir.
So can you write this one as h prime z? H prime?
Yes, sir.
Yeah, why?
Sir, because hx is fx plus igx. Sir, which is dh by dz.
Yeah, so you are looking at the horizontal direction only, right? And you are still getting the whole derivative, right? So that is the, importance of complex derivative, right? So you are looking at just horizontal direction, and still you are getting the complete one, the whole thing. So this is correct. This is correct. So this implies there exists H holomorphic, because H prime exists, right? Holomorphic on omega such that H prime is F. What did we assume? Assume F to be just continuous. But what else? Is this integral depends only on the endpoints. So that implies somehow holomorphicity, right? Isn't this very strong?
Yes.
Yeah. So of course you don't know yet whether f is holomorphic. Once by the end of this my lectures, you will see that the derivative will also be an holomorphic function in some way, and which will be explained in the next set of lectures.
So H holomorphic will give automatically H dash is holomorphic.
H is holomorphic, but how do you know H prime is also holomorphic?
In complex analysis, if one function is holomorphic, then its all derivatives are also holomorphic.
How do you know it?
using the power series.
Well, did you expand power series?
No, we
Not
just look at the coefficients and what is the radius of convergence.
No, but for a holomorphic function, do you still know in this course that there exists a power series?
No, still not.
Still no, right? So you need certain integration for that. It's not automatic. So hence the complex integration lies in between. Okay, so a definition. So a definition which is primitive, right? So you already have seen it. So what is a primitive? Let f from omega, which is a domain in C or open set in C, be continuous if there exists capital F from omega to C such that capital F prime is F on omega, then F is called a primitive of F on omega, right? You see, this concept of primitive is not from complex analysis. It comes from actually real analysis, R2, right? Okay, so what we proved here that. So what we proved, let me state in the form of a theorem. So what did we prove? We proved that if the integral is independent or dependent only on the endpoints, then we have a primitive, right? So if integration over gamma f dz depends only on the endpoints of gamma for any curve gamma in omega, then f has a primitive in omega. So here you see we are looking at f prime, so which means that f is holomorphic already. Okay?
So don't we need the continuity of f in this theorem?
Yeah, I mean, of course, f is primitive, f will be continuity. Yeah, f is continuous. So well, while defining integration, we generally assumed f to be continuous, right? We did not take any other while defining fz. So, but you can mention actually if this one depends on if for a continuous function f on omega. All right. So now, what is the converse of it? Is it true? Yeah. Suppose f is a primitive. What about the integration?
Yes, sir, that depends on the endpoint.
Okay, so that is easy. So let me give it as an exercise. So this is an exercise. So if f omega to c continuous has, so continuous, let me put it right on top, has a primitive in omega, then for any path gamma from AB to omega, integration over gamma f dz is depends only, then so that on the endpoints. Okay.
But this we can prove using fundamental theorem of integral calculus.
No, that is that you have seen it in real variable only, right? You have to take it in that form where you can apply the fundamental theorem of calculus. Okay, that is the what, nothing else.
Okay, but yesterday you gave one exercise that
was also from A to B. F was continuous from A to B to C.
Oh, okay.
Okay, F was not defined on a domain omega. So you have to take this integral in the form of integration over A and AB, interval AB, to certain functions, and then you apply the fundamental theorem of calculus. So just taking this into that form is the work, nothing else. All right. Now, next thing what I would like to, since I have only a few minutes left, let me give some, maybe I was thinking of giving an idea of Cauchy's theorem over rectangle, but let me explain in 9 minutes what is this p dx plus q dy, right? The question is, what is this p dx plus q dy, right? Do you know what it is? Yeah. This is a differential one form on omega. Okay, so the question remains, what is differential one form, right? So the question remains, what is differential one form? I'm not going to use this anymore. So this is for, since I have only few minutes left, and so this is a brief discussion, nothing more. So don't get afraid if you don't understand it properly. It doesn't actually. It's you are not expected to understand in 5 minutes. It needs quite a bit of time. It's just a brief discussion. So here, if you consider a domain omega, domain in C, let's look at C only, R2, yes, R2. Now let's look at a point P in omega. So corresponding to P, so omega is a domain here, P is there. So one can consider the tangent space of omega, right? So what is it? It is isomorphic to R2. It is isomorphic to R2, linearly isomorphic to R2 for each. All right. So this is the tangent space of omega. And since it is a vector space, one can take dual, the dual of TP omega, which is the cotangent space of omega at P. All right. Now what we do is we consider, so you can consider two space here, union of TP omega, P belongs to omega, the whole thing. And similarly, you can consider union of P belongs to omega, TP omega star. So this is also called sometimes TP star omega, which is called the cotangent space of omega. Okay, so this two space. This part is called, this is a notation T omega. This is the tangent bundle, and this is T star omega. This is the cotangent bundle. All right. Now what we do is we look at this. So don't go into the name cotangent bundle and cotangent bundle. You look at, so I look at cotangent bundle only. And so union of P in omega, and this is T star omega. This actually forms a manifold. So this forms a manifold, but we will not go into that. So what we look at is projection pi, which, so it would be P comma any point here will look like a point P and then V star, right? Is a vector in dual of R2. So this goes to P. This is the map, projection map. This P comma V star goes to P. Now we consider another map. We want another map here from here to here, right? So that the composition becomes identity, right? So a map, a smooth map, there is a concept of smoothness, differentiable map. Omega, from here it is omega to this one, this whole object, right? This whole object, which is nothing but T star omega, such that after, if you go via omega and then come back via pi, so pi compose omega is identity on omega, is called a differential one form. So similar thing from the similar thing without star is vector field. Okay. So similar thing without star, that means if you look at tangent bundle, you will get a vector field.
But sir, what is the guarantee of existence of such map?
Well, existence of such map is not guaranteed, but for a domain, you can always do this, right? You have a constant map, right, all the time, right? P goes to P comma constant V star, a constant vector. That can be done. So constant map is there. So an example here. So that is how. So the point is here, each of the component, each TP of this one is actually isomorphic to R2, as I said, right? This is R2. The dual will also be isomorphic to R2. So you will have two components, right? Which is nothing but P and Q. P and Q in the sense that P dx plus Q dy. So any one form on omega can be written as p dx plus q dy, where p and q are smooth map on omega. So you see, somehow this dx and dy forms a basis of this dx at p, so which means this, so dx at p, dy at p, this forms a basis of dp star omega. Okay, and this is the dual basis. This is the dual basis to del by del x at p, comma del by del x, del by del y at p, right? Which is the basis for tangent vectors, vector fields, right? So here, that's how dx and dy comes, and as you move p, this basis would vary continuously. Everything would vary continuously, smoothly. So here, therefore, you get a function p and q, right? Here you are moving, as you move p, it will vary continuously, and therefore, when you look at this linear combination in terms of dxp and dyp, there will be two constants. That constant will move smoothly, and you get a function, and those functions are this p and q. Yeah, so it is 10 minutes. Hopefully, you get a brief idea of what it is, right? I mean, it can't be explained more in complex analysis. Anyway, if you have any question, so I'll stop this today. Next time I'll start with Cauchy's theorem and the winding number.
So any questions from the participants?
If this is one form, so how two form will look like?
Oh, how two forms? It's actually, then you need to look at tensor product and some operation, the quotient of tensor product, to get in two forms. Well, in R2, two forms are easy. It's one dimensional, so it will be spanned by dx OH dy. So, but in general, if you have Rn or if you have manifold, then two forms you will get, taking two tensors and then quotient with some relations, and you get there. So this is nothing but multilinear algebra after this. So if you understand what is one form, the other things are much easier. But this is not a part of the course. This is an extra thing. So you don't need to bother about this. I'm not going to use anywhere. Okay, so but most important thing is that this theorem, which I took most of the time today to explain, this theorem. This is very important.
Sir, in this theorem, you told that only the last part contributes. Can you explain, because it's still not clear to me?
Yeah, because we have chosen the point xy, right?
Why
And
k minus 1 parts don't contribute?
yeah, because where the point xy lies, right? Xy is this point. Xy is this point only,
Okay.
right? And this the domain, this integral depends only on the endpoints, right? So it will depend on this and this, right? So
Yes.
how many times you take whatever curve you take in the middle doesn't matter,
Okay. Okay. Thanks.
right? Is
Yeah.
it
Yeah.
clear?
Thanks. Yes. Yes. Thanks.
Yeah. So the point is, if you go this way, this way, this way, this way, whatever kind of this, ultimately this go this way, doesn't matter. So the point is, since it is given to be depend only on the endpoints. All right. Yeah, maybe I should make this part.
So, if there are no questions, let us thank Dr. Sushil Gorai for a very nice lecture. And I think that one form is new to many students, many participants.
Yeah, so this part I tried to mention as brief as possible.
No, it's very nice. It's not there in the normal textbooks, so it's very good to the participants to learn.
Yeah, hopefully that will. Yeah.
So thank you, Sushil. Thank you.